So we're going to start out with our talk with one of our primary sponsor, Pyreg. We thank you, on biosolids, sewage sludge, and manure with Robert Kovach. Did I say it right? Kovach with Pyreg, and his talk is on sewage sludge carbonation, a future of disposal of sewage sludge. So you're on.
Thank you, Chuck.
Who's our time tracker? Because I don't pay attention to that. We don't have anybody, so we can do better.
So thanks everyone for joining. Good morning. My name is Robert Kovach from the company Pyreg. We'll be talking about carbonization of sewage sludge today. Just a bit of background first on the company Pyreg, short overview. Company was founded in 1999 by our current CTO, founder Helmut Gerber, starting at the University of Bingen in Germany. 2009, we became a company. Pyreg was formed, and we started manufacturing and deploying systems to treat biogenic residues. This led to several iterations keeping the same proprietary technology. But in 2020, we developed a new series PX plant, which we'll talk a little bit about today. In 2022, we're proud to have opened our US offices and formed a subsidiary, Pyreg Inc. Today, we have over 50 plants that we've distributed worldwide and roughly 100 employees. So today, my presentation is about the carbonization of sewage sludge, but the topic reaches far beyond the technical aspects. The broader point is the paradigm shift, and this involves thinking of waste as a resource and part of a circular economy. Waste is a resource that is simply in the wrong place and not being utilized properly. But where does the circular economy start, and what does it look like? What starts here? That's what it looks like. But this is the start of the biosolids biochar circular economy. However, when we look into this portal, we have a flush and forget mentality. We look downstream at the wastewater treatment plants. We see sewage sludge disposal problems, high transportation costs, high tipping fees, mass reduction in processing costs, legacy wastewater treatment plant infrastructure that will require significant costs to upgrade, environmental contamination. We all hear those acronyms that I was told to say what they mean. PFAS, PAHs, dioxins, pharmaceuticals, and microplastics. So polyfluorinated substances, polycyclic aromatic hydrocarbons. This is what's inside of the sewage sludge. But we need to look at shifting that paradigm. And the carbonization of sewage sludge, we can address these problems as opportunities. And we can turn that waste into a valuable resource, therefore shifting the paradigm. We've all heard the term flushing money down the toilet. However, by producing biochar from sewage sludge, we can demonstrate waste to value and drive a true circular economy. So why biochar? Why would you carbonize sewage sludge and create biochar? For enhanced water contamination mitigation, improved nutrient and waste management, stormwater treatment and water quality in general. Of course, we'll talk a bit about this, a big theme here for all biochar, and that's biochar carbon removal, and a renewable energy objectives that through the process of carbonization, generating green energy, and of course the positive economic impact for the wastewater treatment plant industry. This isn't simply processing waste and seeing it as a cost, it's seeing it as a business opportunity, and that's what we'll dive into today. We got a long way to go and a short time to get there, so at the end of the day, if I don't answer questions or get to your points today, please feel free to stop by our booth 400 and see us. We'll be happy to address your questions. Why biochar? It's why we're all here. I talked about the circular economy first, waste management. There's the carbon economy, eliminating CO2. There's the new energy economy, using the production of biochar to generate green energy. And of course, there's the regenerative agriculture economy, and biochar sits firmly in the center. But what's the justification for carbonizing biosolids? It starts with looking at natural resources. You probably all seen a diagram like this, but I'll call your attention to the upper right-hand corner, and I'll make this statement. No phosphorus, no food, period. Green plants need phosphorus as a fertilizer, and biosolids are filled with it. And here, interesting, 80% of the world's phosphate reserves, where are they located? Morocco, China, Jordan, South Africa. That curve, and there's many diagrams like this you can find online, but it's basically shown that at 2050 and beyond, the available phosphorus or phosphate rock resources to make fertilizers like triple superphosphate will decline. Again, no phosphorus, no food. But we have an opportunity in front of us that we're looking at as a waste today that's really a value. Take a look at this here. This is just, we looked at it last year, we'll look at it again this year, but this is a 3-year plot of phosphate rock prices since 2021 through middle of last year. From under $100 per metric ton, now 342 as of July of last year. That's obviously showing you what supply and demand mean. And when you have to transport 80% of that phosphate rock to become fertilizer outside of those nations. So we did some tests at Pyreg. This particular one here, you see, that was done actually a little over a year ago. And what it did, long story short, you can see you'll see the results, and we can go into detail. But we produced biochar from biosolids. We had roughly 500 degrees C in our pyrolysis process, and we could show that organic hazards such as PFAS and PAH were below EU detection limits for the chemical compliance with European Union legislation. But more importantly, this control test, what was it doing? It was taking triple superphosphate, a control, and then applying the triple superphosphate to plants. It was applying the biosolids-based biochar to those plants, beginning the percentages in the soil, and then measuring the plant growth, and then measuring the phosphorus that was retained in those plants as uptake. At the end of the day, very simple here. Of course, the study goes much deeper, but this is a comparison showing a 90% efficacy in comparison to triple superphosphate. So we can dig stuff out of the ground, and we can fertilize, where we can take biosolids-based biochar, and you have excellent results in the effects. And of course, I won't go into this today, but it's the theme that runs through everything that we're talking about here during this conference, and that is sewage sludge biochar, or properly produced biochar, as a stable carbon sink. And yesterday someone put up there and said, hey, I'm going to be conservative, and I say it's more than 300 years. Is it 1,000 years? Is it 1,000,000 years? Is it 3 million years? The bottom line is, what you see in these ongoing studies is that biochar sequesters carbon and is a durable CO2 reduction possibility. So a little bit about the Pyreg technology. Won't go into too much detail here, but basically we take a variety of different residues. You can see in the center here, multi-material capable. That could be woody residues, that could be mixed residues, that could be agricultural residues, digestates, manures, or sewage sludge. Put the Pyreg system as close as you can, right at the wastewater treatment plant. In this particular case, avoid that transportation distance, dry the material, and at the end of the day, producing biochar that could be used in agriculture or could be used in building materials, using the renewable energy from our systems to help with the drying process, and of course, creating CO2 certificates. Advantages of the system: it is autothermal. It is a continuous process, not a batch process. and it is a highly automated process where we're giving a significant amount of feedback to the operator. Here you see the process here. I'm not going to go into a lot of detail, but we call this carbonization because we have a two-stage process. In the first part of the process, we're heating up the reactor, which you see in the center, and this reactor is heated with external energies such as propane or natural gas until it reaches operating temperature, at which point the dried material will enter the reactor, and as that material starts to carbonize and the biochar is formed, which you see extracted at the bottom of the reactor, the off gas or the syngas is moved through a process gas filter. And you'll see a picture of that later. It's automated, where we flush that gas stream with an inert nitrogen, and we're controlling the dust, and that syngas is then moved into what we call the flux burner. And flux stands for flameless oxidation chamber. So we're moving from temperatures in the reactor from roughly 500 C to 750 degrees C into the flameless oxidation chamber, where that syngas is being oxidized at temperatures over 950 degrees C. But it doesn't stop there. Now we have a significant amount of renewable energy, and we drive that across the outside jacket of the Pyreg reactor to keep the autothermal process. And it's a symphony, because everything is controlled with sensors and feedback. So the speed of the screw, the dwell time, the temperature, all are being controlled to carbonize that material, and then we're going to have a significant amount of energy left over. So that thermal gas stream is then moved to what you see at the top left-hand corner of the diagram, which is a heat exchanger. And there the customer can say what type of energy or how they want to receive that energy. Do they want to receive it as hot water, which they could use for drying? They want to receive it as steam. They want to receive it as electricity through an ORC. In this particular case, with biosolids processing, that's normally going to be hot water, because that energy is then going to feed a dryer upstream to dry those biosolids, which we'll show a bit later. Simple input material requirements. Obviously, sizing is important. No less than 3, no greater than 30 millimeter particle size. Not a problem for sewage sludge. A flocculant would be used in order to, let's say, clump that biochar, that biosolid material before it reaches the Pyreg reactor. It needs to be pourable and free-flowing, and it needs to be at least 80% dry. In the applications that we have at sewage sludge treatment plants, normally it's 90% dry when it enters the Pyreg reactor. One important point, though, is that calorific value. And it comes into play, is the sludge digested before? Had it gone through an anaerobic digester or not? And to look at a minimum of 10 megajoules per kilogram as a calorific value. And pay attention always to the fine print below, because acidic components, chlorine, sulfur, are very important considerations, and this is why you'll see for our particular systems that we produce for sewage sludge applications, we have integrated wet scrubbers and a activated carbon filter, because as we know, the stuff that goes in there is the nastiest type of material that you can process into biochar. This just gives you a quick schematic of what a Pyreg system looks like. They're modular, scalable. It's about the size of a 3-car garage. The modules are tested at our facility in Germany, where they're manufactured prior to being packed up and shipped to the location. Once they're there, it's simply like Lego blocks, putting them together and bringing them into operation. To put them into operation, other than having the foundation and roof, you would need electrical connection and external connection for energy such as propane and water to quench the biochar as it exits the reactor. Just some quick stats, and you can get information on this. It's not a sales pitch for Pyreg. It's giving you 2 different systems here, a PX500 and a PX1500. The 500, we had this for many years. We started in 2009 manufacturing these. We don't really manufacture them for biomass anymore as we do biosolids. And why is that? Well, when you start out with something that is essentially liquid and you dry it, you have a significant reduction in mass. And when we get that material after it's dried and it enters the Pyreg reactor, it's essentially 90% dry, and then we can convert that. So mass reduction is a big part, and these smaller PX500 units fit really well in roughly a 50,000 person population equivalent. That's kind of a sizing, if you will, for the type of system. But you can see here, we look at the annual throughput. This is dried material under the conditions mentioned below, but you're looking at roughly 4,000 tons of dried biosolids with a 1,500 and an output of about 2,400 tons of biosolids-based biochar per year. I'm not going to go through these USPs one after another, but I will highlight a few. Automation is really important. Feedback to the operator. This isn't somebody sitting there at the machine turning dials and wheels and saying how much oxygen comes in and what temperatures should we monitor. There's a feedback to the operator. The operator can monitor on a handheld device. Once that operator is skilled enough, we see many of the wastewater treatment plants where they're monitoring the process, and as long as the dryers are drying and the feedstock is entering and the biochar is coming out, it's an automated process and runs as it should. The other points are the durability. We're not talking about wood here. We're talking about material that is highly acidic, that has heavy metal content inside. The type of reactor material that we use, the components that we use, they're durable. They were made for that type of environment. It's just a different world with biosolids that you will find with other equipment, and not having the right materials just simply won't stand up to the aggressive nature of biosolid material. Is the technology proven? I'm not going to dive into every one of these, but what I wanted to impress upon you today is do the research, make sure that you can point to why is the technology proven, and use academia and not having Pyreg doing the tests themselves, but large organizations. And remember at the beginning of the discussion I mentioned to you what some of these are. So, pharmaceuticals, microplastics, PFAS, largest study was EPA that was done back in 2020 at a facility in San Francisco, the Silicon Valley Clean Water Authority. This is the biggest one online I would point you to. It's basically used by anyone and everybody in the industry at this point. Feedstock pollutant testing back in 2013, University of Aachen and Halle, looking at PAH reduction and over 99% through the process of carbonization, and feedstock pollutant degradation, dioxins, having done a test and actually pulling out organic matter and testing it in an area where the dioxins were reduced. Heavy metals reduction actually in the biosolids itself. What's the takeaway from this side? Higher temperatures will remove more cadmium. Cadmium will be present. It will be vaporized. Some of it will be in that exhaust stream. It needs to be captured. This is why we have the activated carbon filter. But notice the point here, that when you have higher temperatures, you will remove more cadmium, but as you increase those temperatures, you will have less plant available phosphorus. And that's what you see on the scale to the right. But look at triple superphosphate in there. It has its share of cadmium in it already. And so stuff that we're digging out of the ground that's part of fertilizer already has a significant amount of cadmium in it. And actually treating at high temperatures this biosolid material, you can reduce the amount of cadmium. But we still want to keep plant available phosphorus in that biochar. Last point here, when we think about sludge, think about this. If you're going to take one thing away about circular economy today, imagine this. You have PFAS-infested area. You have sewage sludge. You process the sewage sludge, you create biochar. That biochar can work as a sorbent. And actually, in a great study that was done in Europe, you can find this information at EBI, is what you see here on the next slide, is because of that pore structure of biosolids-based biochar, it absorbs PFAS very well. So think of it as a soil remediator. There was a great study done at the airport in Oslo where they said, well, we got a sewage treatment plant here. We're going to make biochar. We're going to take that biochar. We're going to take it next to the airport runways where we were using fire equipment for years, this foam that had PFAS in it, put the biochar into the ground and measure what that biochar did in removing the PFAS. That's circular economy. You could then repurpose that biochar back through the pyrolysis process, and you've got an ongoing PFAS destroyer, destroying it in the biochar as you're producing it, as you're the biosolids as you're producing the biochar, and also using it as a sorbent. Going to run you through some quick pictures because I got the 1 minute sign here, but this is just the process. A wastewater treatment plant. You have anaerobic digesters. They're powering a micro turbine. You've got a dewatering press. After that material is dewatered, you're going through a belt dryer. That belt dryer is being fed from energy from the Pyreg system. The Pyreg system carbonizes or mineralizes, and at the end, what do you get? A phosphorus fertilizer. And scavenge the energy. Those little red lines there, at every part of the process, scavenge that energy to use it to help other processes. So I'm going to take you through a bit of picture here. This is in Kleve, Germany. This is a purposely built site for pyrolysis. They didn't have these buildings here before, but they said, we're going this route. And they didn't talk about selling the biochar or doing anything. This was about the cost avoidance element of it and proper waste removal. But you can see a project like this is not just about we pop in a Pyreg unit or another unit to do pyrolysis or carbonization at this site. There's periphery involved, there's engineering involved, there's very strict adherence to the input material. Make sure that you keep it cohesive. But you see the dewatering screws up above on the left-hand side, upper left. Below that is the dryer. You can see that Pyreg system about the size of a 3-car garage packed in there on the right-hand side. There's the Pyreg reactor with the automation, giving feedback directly to the operator, fully automated. And there's that filtration system up top. You can see we're taking ambient air, generating nitrogen, and flushing to address dust. And then here you see the pictures of the wet scrubber on the far left and center, scrubbing the acidic components out of that gas stream. And then to the far right is the activated carbon filter to protect against mercury and cadmium. And that's the end process. Next installation will be in Ephrata, Pennsylvania, ongoing. You can read a lot about this online. I'll just give a shout out to our partners there, Bioforce Tech and GHD, who wrote the study. I put it here as the source. You can read how that wastewater treatment plant did an analysis and why they chose carbonization of their material versus doing an upgrade to their existing infrastructure. So I know I'm right at time, so I guess I'll stop there and open it up for any questions. Thank you.
Let me grab that mic. John, you want to run around? See if anybody has any questions. Why?
So your biochar that comes out of the Pyreg, any idea what the carbon content of that is? Just curious.
It tends to be relatively low. Obviously, we can't make carbon in the material, so we look at, for instance, with wood, where you get, 80% plus, you're, down 50%, and even lower than that with biosolids-based biochar. Okay. It's going to have a much higher ash content, obviously, in the material, but at the end of the day, you can convert at much higher rates. So think about that. If you're converting biomass, wood, maybe you get 20 to 25% conversion rate, whereas with sewage sludge, you can get upwards of 60% conversion rate. So thinking about processing of biosolids, think about conversion rates as well.
Hey, thanks. I was just wondering, when you were talking about the cadmium, were you finding at lower temperatures that it was free cadmium available for leaching into the water, or were you seeing that it was bound in the char, but still noticeable?
The particular cadmium that we're referring to is, obviously we're reaching reactor temperatures. In this case, we were showing around 500 to 600 degrees. So in that syngas stream that then is moving to our flameless oxidation chamber, we're talking about that cadmium that is still available. We can't let that go out through the stack. And I think it's an important point for everyone to keep in mind. Processing the biochar, the biosolid itself and making biochar is one thing, but then controlling that emissions is an entire other game. And if you don't take into account how you control those emissions, this is danger for the industry, and this is why it took a long time for us and our partners here in California to put that facility at the Silicon Valley Clean Water. Emissions is a big part of carbonization or pyrolysis of biosolids.
Okay, thank you.
We'll take this last one so we can try to stay on schedule here.
Yeah, it's not actually a question. I just want to add in on the heavy metal aspect. You can't avoid heavy metals with sewage sludges, and there are several ones that will not be evaporated by these temperatures. And every heavy metal that is remaining in the sludge is actually sort of locked in the sludge as it acts like an activated carbon. And there has been extensive studies showing that you can't leach these heavy metals from sewage sludge biochars. So that maybe answers the second part of the question.
Okay, thank you. Round of applause.
Thanks, everyone.
Biochar.org appreciates the support of our sponsors, exhibitors, presenters, and attendees. We look forward to seeing you at our next conference in September 2025.